Automating complex tasks often means writing rigid scripts that break easily when things change. What if we could define workflows more flexibly, allowing AI to dynamically guide the process? I've been developing an AI-powered workflow orchestrator to tackle this challenge. In this first video, let's dive into the core of it: how these powerful and adaptable workflows are defined using simple, human-readable files. Okay, let's explore how that works. On the left, you see I've opened a folder named Workflow. This is where we'll store and define our workflows. Each subfolder within this main workflow folder defines one complete workflow. Let's examine one workflow example. Each workflow starts with an index, MD file. This simple Markdown file has only one mandatory section, the step section, which we'll look at next. Besides the step section, you can add any other content you like, placing it either above or below the step section. This additional content isn't structured into specific sections, but serves as general guidance, context, or overall objectives for the orchestrator. For example, you might include a goal description here, but it's entirely optional and freeform. The crucial, mandatory part is the step section. Inside Step, you'll find a list defining all the individual steps that make up the workflow. Now pay attention to this list. We have links here. Each item in the list is actually a link pointing to another Markdown file using a relative path. This link tells the system which file defines the actual step. And importantly, the text inside the link's brackets serves as the name for that step within this workflow. This design allows you to reuse steps you've already created, perhaps stored in a shared folder or even defined in another workflow, simply by linking to them. So here, for example, we have several steps listed. Something important to know: the very first step listed here is always the starting point when you initiate the workflow. So the orchestrator begins by executing this first step. After that, instructions within each step file will guide the orchestrator's decision on which step comes next. So, while steps can run sequentially as listed, they don't have to. The real flexibility comes from the guidance within each step, which dictates the actual execution order. And that's a key part of the power behind this MCP server orchestrator. Now let's look at how an individual step file is defined. A step file must contain two mandatory sections. First, Orchestrator Guidance. This section provides instructions in natural language to help the orchestrator decide what to do next, based on the workflow's current state, context provided by the client, and so on. The second mandatory section is Client Instructions. This defines, again in natural language, the specific tasks the client application must perform for this step. These are the explicit instructions for the client application. Then you can optionally include other sections, like a goal section within the step file. Again, this step-specific goal helps the orchestrator understand the context and purpose of this particular step. Let's quickly recap how this executes. When you run a workflow, the orchestrator first identifies the corresponding folder. It loads the index, MD file from that folder. Then, it follows the links in the step list, reading and appending the content of each linked step file. It effectively combines index, MD, and all the step definitions into one large context. The orchestrator receives this combined text. Using this combined text, the orchestrator prompts a large language model. The LLM analyzes the current situation and uses the orchestrator guidance for the current step to decide what the next step should be. Based on its decision, it outputs the name of the next step. If that step name is valid, the MCP server's execution engine confirms the transition to this new step. The engine then retrieves the client instructions directly from the file of that newly chosen step and sends those instructions to the client. This creates a robust mechanism. The LLM's primary responsibility is simply to decide the name of the next step based on the guidance. The actual client instructions depend only on the step file chosen by the LLM. Now, this core design choice, decoupling the orchestrator's decision-making from the agent's execution, unlocks significant advantages. It reduces the cognitive load on the executing agent, significantly increasing the reliability that it will follow the specific client instructions accurately. This structure also mitigates common LLM issues like bias or the tendency to rush and skip steps when context grows large. Because the orchestrator maintains a stable, focused view of the workflow structure, it ensures the process integrity is upheld. This decoupling also opens up possibilities like using different LLMs for each role. Perhaps one optimized for reliable, focused decision-making, like following Orchestrator Guidance for orchestration, and another, potentially larger model optimized for complex task execution based on client instructions. Additionally, by strategically incorporating save-resume steps, the executing agent's context can be actively managed. This architectural pattern is crucial for handling very complex, long-running workflows that might otherwise exceed the context limitations of a single LLM or require different, potentially less flexible, automation tools. Okay, let's move on to see this in action. So, we're still here in the VS Code IDE. I'm going to use the Klein AI Assistant. Here in Klein, I'm working with a demo project created just for this demonstration. And I'm going to give it this task. Use the workflow named Refactor to rename a function currently called CalculateSum to add numbers. So, just a simple function rename. Klein, the AI assistant, will interpret the user's request. It knows about the tools available to it, including the Orchestrator MCP server tool. So, it understands its goal is to call this orchestrator tool to start the workflow named Refactor with the specific task of renaming CalculateSum to add numbers. Notice the prompt is quite imprecise. I did this deliberately. It shows that even current, cost-effective LLMs can often understand this kind of ambiguity, which is promising. So now, Klein attempts to execute the workflow using the start workflow command. Initially, Klein fails because the workflow name Refactor is wrong. But watch this. The LLM sees the error, lists the available workflows, finds the correct one, refactoreth test, and automatically retries. This time, it succeeds. Upon success, the orchestrator creates a workflow instance with a unique instance ID. This ID is important. It allows us to save the state of the workflow. If we stop and want to restart later, we use this ID to resume exactly where we left off. It also helps in logging everything that occurs within this specific run and ensures we always pick up at the correct point. Essentially, it manages the workflow session. Okay, so what happened when the workflow started successfully? The orchestrator recognized the start event. It determined the next step should be the first step defined in that workflow's index, MD file, which, as we saw earlier, is locate function. The orchestrator responds by sending Klein the specific client instructions for the locate function step, taken directly from the step's definition file. Context, including the original and new function names, is also passed along. So, Klein sees the response from the orchestrator MCP server is valid. It considers the workflow successfully started. Now it reads the received instructions, understanding it needs to locate the function CalculateSum. It proceeds to follow these instructions. Now, for demonstration purposes, I've intentionally included instructions here that might cause a small mistake, so we can see how the system handles imperfect execution. So, Klein reads the calculator, py file. It finds the CalculateSum function. It then calls the MCP server again, reporting, "Okay, I've located the function in this file. Here's the file path, the starting line number, and the ending line number." Okay, so the orchestrator server receives this update. Next, Klein reports the successful function location back to the orchestrator and asks to advance the workflow. The orchestrator checks its guidance, confirms the locate function step is complete, and instructs Klein to proceed with the next step, apply rename refactoring. So, having located the function, the next logical step is to actually rename it, applying the refactoring. Klein receives the client instructions for the apply rename refactoring step. It applies the refactoring, following the instructions precisely. However, these instructions intentionally only cover renaming the function definition, not the call to calculate some elsewhere in the main part of the code. So, the code is now broken. Again, this is intentional. Breaking the code here demonstrates a key capability: how the workflow handles and recovers from errors caused by incomplete steps, ensuring the final result is still correct. So Klein calls the orchestrator, reporting, "Okay, I've performed the refactoring actions." So, on the successful attempt, the orchestrator sees the apply rename refactoring step was executed. It tells Klein the next step is check for old reference. The instructions specify using a script provided at a certain location. This script searches the entire codebase for any remaining instances of the old function name, calculates them. The script will return its findings. Klein sees the instruction to run the script. Klein runs the script and it executes successfully. The script returns its results. There are still 5 places where calculateSum exists in the codebase. So, Klein reports this back to the orchestrator. I found these remaining references to the old name. The orchestrator receives this. Since references still exist, the renaming task isn't fully complete according to its logic. Now, watch how the orchestrator handles this, based on its guidance for the check for old reference step, which dictates looping back if references are found. It directs Klein to execute the apply rename refactoring step again. Klein receives this instruction and understands it needs to rename the remaining references it just found. It proceeds to correctly rename all the remaining instances of the old function name. It's finished. Then, Klein reports back to the orchestrator that the refactoring is done. From this point, the workflow proceeds smoothly through the validation steps, checking again for old references, running tests, and committing the changes. Nothing really interesting happens, hence to keep things moving and make the viewing more pleasant, we'll accelerate the video footage here until we reach the final notification. Finally, the workflow reports the result back to the user. The instruction is to use the notify command via the MCP server. Klein executes this, sending a notification summarizing the successful refactoring, test results, and commit details. This hints at powerful capabilities. Recent experiments using similar automation techniques showed the potential to process hundreds of development tasks daily. Scaling this with multiple workers and evolving LLMs clearly points towards automating a vast amount of development work by defining tasks and workflows effectively. I hope you found that demo insightful. The task finished successfully. With the successful run complete, let's quickly look at one more scenario demonstrating how the workflow handles edge cases. I'll start a new conversation and ask it to refactor the same function again, but remember, it's already been renamed. I haven't reset the files to their original state, so I ask it to refactor calculateSum again. What will happen? The AI will try to locate calculateSum. It won't find any instances. So it will report back to the orchestrator. I couldn't find any references to calculateSum. The orchestrator's guidance for that situation will likely say, okay, in that case, proceed to the final notification step and report what happened. And consequently, we'll see Klein send a notification, similar to before, but this time stating, task could not be processed. Error. The function calculateSum was not found. So that just demonstrates handling edge cases, even with a simple workflow and project. But I assure you, this approach scales to more complex projects and tasks, especially leveraging powerful models. This approach represents the future of development. I expect that within months or years, many routine software tasks will be automated using systems like this. Now, perhaps not for monolithic, massive codebases immediately, but for modern architectures like microservices or well-defined components with clear specifications and READMEs, AI will be able to automate many tedious development tasks like testing and documentation. All these tasks that are currently very time-consuming, tedious, and consequently often neglected when handled manually. This will truly revolutionize software development. As you've seen, this workflow automation offers immense potential. It's poised to fundamentally change how we build software, moving beyond just saving time to enabling entirely new levels of efficiency and quality. I'm actively developing this MCP server in my free time, so it's still in its early stages. I believe community involvement is key to its success. I welcome feedback, contributions, and collaboration to help improve this server and explore its full potential. Get involved and let's explore these possibilities together. Thank you.